Welcome back. Today's agenda is to talk about high speed and robotic assembly. In the past, we have spoken about design for assembly mostly from the manual assembly perspective. Today, we will see how those concepts differ or are adjusted for high speed or robotic assembly. Oftentimes, robotic assembly becomes important in today's case, especially in mass manufacturing. So, it becomes imperative to discuss about the concepts that leads to analyzing and assessing robotic assembly and its efficiency. There are a number of charts and examples that will be shared in the rest of this particular presentation, which are picked from our textbook by Dewhurst. So, very similar to the design for manual assembly, where we spoke about symmetry, size, weight, thickness and some guidelines. I am going to present you few cases here where I will try to compare and contrast what is the difference between manual assembly and robotic assembly from a component perspective. So, if you look at this two threaded stud here, you can see that there is a lack of symmetry in this stud compared to this stud. Okay. These are basically the threads here, okay. And this is a symmetric thread and this is a asymmetric thread. There is a slight lack of symmetry. In terms of handling, from the handling perspective, there is no big difference in handling these two from a manual handling perspective. However, if you are going to use a robot and the robot has to distinguish between this and this. Let us say this was thread, this is a stud A and this is stud B, or family A and family B, and the robot has to, or the automatic assembly system has to distinguish this from this. It requires an expensive vision system or an equivalent system that will have to find out that this thread is asymmetric from this. Okay. So, in such cases you cannot use the same rule that was used for the manual assembly. That is where the difference between manual assembly and robotic assembly comes into picture. This is just one case. If you recall, in the manual assembly, we were predominantly interested in the time perspective. Here also we will be interested only in the time, because that is exactly what the advantage of mass manufacturing, wherein the robotic assembly comes into picture. But the time was influenced in the manual assembly by factors such as grasping, orienting and inserting. We used two quantities, if you remember, one is handling and the other one is insertion. Handling is basically grasping and orienting, and insertion again is orienting and insertion. Plus, of course, we have a labor time there, the labor cost basically, that will govern the total cost. However, in the automated design, the basic assumption is if a component can be handled, you can safely assume that it can also be inserted. So, that is what is pointed out here. So, automatic handling, and we really do not consider the insertion into the assembly, it is only the handling part of it. Okay. If a part can be handled automatically, it can be inserted automatically, that is all. So, there is no distinguishing. Okay. We are not distinguishing handling and insertion. So, the design for the ease of orienting and feeding is the other thing, okay, because the feeding, basically there is a feeder rate and all that, which we will discuss next. Okay. So, basically what is the assembly cost is the rate at which the machine cycles. How many assemblies can the machine produce over a period of time? That is what is your assembly cost essentially from an assembly perspective. Okay. Now, I mean, we are not talking about the material cost and all that, the assembly cost. So, how do we quantify this robotic assembly or an automated design? I hope you recall how we did this in the manual assembly by using the Boothroyd chart. Okay. It was all in terms of, finally it will all boil down to the time, and there will be a labor cost that is associated. So, you multiply the labor cost with the total time for the assembly, and then that will give you the total cost that is involved from an assembly perspective, excluding the material cost. So, here how are we going to look at the cost of feeding and orienting the parts? Obviously, the first one is the cost of the equipment, and when it after the equipment cost is taken care of, from a productivity perspective, what matters is the time interval between the delivery of the successive parts. So, I assemble one part, I assemble two parts, irrespective of whatever the assembly procedure is, the time between the part 1 and part 2. Okay. The time interval between the delivery of successive parts. So, 1, 2, 3 successively, and of course, it should be the finished assembly. Okay. So, in order to come up with a number or a formula that relates this, using some simple math, there is a relationship that is provided, that is, this is the cost of feeding. CF stands for cost of feeding. It is some 0.03 times 60 is basically the parts, okay, the second minute conversion. FR is your feed rate, parts per minute, times CR, which is the relative cost factor. Basically, it is the cost that is incurred for using the equipment. See, oftentimes when people want to do tests, okay, in many of the institutions, the cost is only for the equipment usage. So, if my equipment is being used for 20 minutes, this is what the cost is. If the equipment is being used for n minutes, this is the cost. Okay. So, basically the cost of using the equipment rupees per second. Okay. So, this is the cost of feeding that we are looking at. It is a product of two things, one is the relative cost factor and the other one is the feed rate. So, basically there is a relationship between the feeding cost and the feed rate. So, the feeding cost, okay, so the feeding cost is inversely proportional to the feeding rate. Let me make sure that this is the same thing. Yes, the feed rate is that, and the cost of feeding is I have used FC, but CF is the one that I have used in the cost of feeding. Okay. So, the feeding cost is inversely proportional to the feed rate, and oftentimes the feed rate is also governed by the capacity of the machine. Sorry, yeah. So, it is inversely proportional. Sorry, the feeding cost was inversely proportional to the feed rate. The feed rate is oftentimes governed by the capacity of the machine and how many components you want to make in a given time. Okay. Sometimes the machine capacity is higher, but we do not want those many components. So, we try to reduce the feed rate. And of course, it is proportional to the feeder cost. Okay. The rate at which you feed is what the feeder cost is. For otherwise identical conditions, what I mean by for otherwise identical conditions means this is for the comparative purpose. So, the complexity or the simplicity of the design part, the geometry, everything remaining the same. What it means is, it would cost twice as much to feed each part to a machine with a 6-second cycle compared to a 3-second cycle machine. So, 3-second cycle means what? Let us say that it takes about 3 seconds to feed, do the assembly and eject one component, and there is another machine that takes about 6 seconds. So, in 6 seconds this machine will do 2 assemblies, whereas this machine will do only 1 assembly. So, it will cost twice as much to feed each part in a 6S compared to a 3S cycle. Obviously, there are other this cycle this machine is supposed to be expensive than this machine, but your productivity rate is much higher. So, in that sense, the cost is twice in this machine compared to this machine. Hence, your machine specification will obviously be in terms of what would be the cycle time, and it would cost twice as much to feed a part. So, this is interesting, okay, to feed a part in a machine that costs rupees 2y compared to a machine that costs y. Okay, that is kind of, you can see that as a machine cost as well. So, it would cost twice as much to feed a part in a machine that costs 2y compared to a machine that costs y. So, if there is a machine for 100 rupees and there is a machine for 200 rupees, it takes 2 rupees to feed a part in a machine that costs 200 rupees as against 1 rupee for a machine that cost 100 rupees. And of course, that will have an impact on the cycle time, hence your total productivity, hence your total cost. Okay. This is what we spoke about, right. So, inversely proportional to the required feed rate, that is what we saw here as the first one, and proportional to the feeder cost. So, if your feeder cost is less, then the cost is going to be less, if and it is the other way around. So, to understand the relationship, I mean it is a linear in this case, feeding cost versus feeding rate. We have used this particular chart here or figure here. So, the x axis is your required feeding rate, which means parts per minute, how many parts can you supply in a minute in that machine, and your y axis is your feeding cost. Since it is taken from a North American textbooks, it is in terms of cents, but you can convert it to rupees or any currency that we are talking of. Okay. So, this is what the relationship is, right. So, this is the inverse relationship that we are talking about, meaning if you can increase the feed rate, your feeding cost will go down, meaning within a given minute, if you are able to feed more components, then your feeding cost is coming down. That is what it means. The assembly is happening quickly, that is what it happens, and that is what it means. But does it mean that I can just keep on increasing my feeding rate and the cost will? No, there is some kind of a saturation point here. There is a limit to the feed rate, right. So, you cannot, again, you can put a robot to keep on doing it, but there is a limit to that. If your FM is 10 parts per minute, and if you want to do like 5 parts, which is at this level, okay, you do not want the machine can operate at this capacity, but for whatever reason you do not want to operate at that capacity, then what you do is you operate it at half. Then what happens is there is a lower feed, means there is a higher cost that is associated, because whatever, for whatever reason the cost is higher in that sense, okay, from a productivity perspective. But what is the cost of feeding? This is what we said, like 100 rupees, 200 rupees, 1 rupee, 2 rupees. So, what is that cost of feeding? So, just in case your FM was less than your FR, what is this FM? FM is this saturating, whatever you can call it, as operating at the maximum, that is what your FM is, right. So, if you are talking, what if this FM was less than your FR? What is your FR? FR is nothing but your feed rate. Then use greater than 1 feeding machine, that is what it says. So, what it says is, imagine that this is the other way around. So, your FM is 10 parts and wait a second, your FM is 5 and you want 10. Obviously, the only way that you can do is you use greater than 1 feeding machine. Okay. The feeding, in that sense, the feeding cost becomes a constant per machine. Okay. So, we can kind of write this in this sense, is basically 0.03, the same constant 60 times. Instead of FR here, you are going to put FM, and then accordingly the CR is there. Okay. So, instead of FR, we are replacing it as FM, and FM is primarily the 1500 times. This is nothing but your conversion from minutes to seconds, that conversion, times E over L, where E is the orienting efficiency. Can I just take it and put it, or will I have to orient it some way? We will discuss what that orienting efficiency is, and L is your overall dimension that you are talking about. Okay. And in this particular case, we are assuming a feed speed is about 25 mm per second. So, what is this E and L? How do you get this E and L? Okay. So, you assume die that we are talking about, okay. Let us say. So, if you can, obviously it has 6 phases, and let us say I do not care which phase you are supplying to the assembly, okay. Then there is no orienting part to it. Okay. However, let us say that I have these marks on the die, and then okay. So, I have these marks in the die, and for whatever reason the assembly requires a particular phase to be supplied for the assembly part. Then what happens is, if you are just going to use the die, probably it will take about 1 second, let us say. But if I have to use some kind of a vision system to understand whether there was 1 dot or 6 dot or 2 dots, then I have to orient the die in 6 different directions to understand how many dots are there, and then supply that phase of it for the assembly part of it. So, it will take about 6 seconds for me to identify the phase and then orient it. So, it is going to be, if only side 6 is to be selected, or it can be any side, okay. A vision system need to be used, and then you can only do 1/6 per second, that is all you can do or it will take 6 seconds primarily, that is what it means. So, if the dies were twice as big, it takes twice as long to deliver. Okay. So, smaller the better it is. If it is larger, then how much ever geometrically it is larger, that much longer it will take for the same machine capacity. Yeah. Now, it is very similar to the Boothroyd approach, where we used 2-digit code, if you remember, and then the first digit was for handling, and the second digit was for insertion. In a similar fashion, we are going to develop some kind of a coding technique here, from which we will get some time that is associated with the assembly procedure. So, basically we are going to look at the feeding rate, and L will be known, right. So, we know what the feeding rate is, and we know what the dimension of the component that we are trying to assemble here. What we need to figure out? We need to figure out E and CR. Let us see. Okay. So, we are looking at here primarily we need to figure out this E and the CR. L is known. Okay. So, and FR or FM is also known. Okay. So, it is basically a 3-digit code. So, there are 3 digits. What is the first digit? It is dependent on whether your component is rotational or non-rotational. And if it is non-rotational, the question is whether it is flat, long or cubic. So, basically what happens is you do this A over B. I'll just quickly tell you what your A or B is. Okay. So, yeah. So, we will discuss this example, however, I am just showing you. Okay. So, this dimensions, okay, you can only have 3 dimensions, right, meaning like if you are going to put a superscribing cuboid around it, then A, B and C, right. So, based on, and then it will be clearly given here. See, if you go, if your component was like this, what is A, what is B, what is C is given. So, it is usually the length, width and your thickness, that is the way. And if it is like this, then it will be kind of an L by D ratio, okay, if it is a cylindrical stuff. So, if it is cylindrical or disc, you are going to look at your L by D ratio. If it is greater than 0.8, then your digit is 0. If it is a short cylinder, it is 1. If it is a long cylinder, it is 2. Similarly, if it is non-rotational and it is flat, then what is A by B, what is A by C? Long means it is just A by B. C is the third dimension is negligible, and if it is cubic, then A over B and A over C, these are the conditions, right. So, depending on it you will get. So, now the next 2 digits are going to be divided into 2. The first one will be based on if your first digit is 0, 1, 2, and the second case is, so your first digit, if it is 0, 1, 2, there is one case, and if your first digit was 6, 7 and 8, there is a second case. So, we will see what it is. The second and third digit, if the first one was 0, 1, 2, what was your first one? It meant that it is rotational, that is what it means. So, this is what. So, the cylinder is a rotational and this is a non-rotational, just for clarification purpose. So, if your first digit was 0, 1, 2, this is how to read the chart. Okay. The chart is available like this. How do you read? there are 2 columns as against what we saw in the manual assembly chart, because there is only 1 column would have been there, right. So, in this your second digit and your third digit, there are only 2 digits, in this we have 3 digits. Obviously, the first column belongs to the E and the second column belongs to ER. These are the 2 things that we wanted to capture. For instance, you know the alpha symmetry and the beta symmetry. The idea is the same from the manual assembly concept. So, the question is, so if your first digit can be 0, 1 or 2, I have just cut it here, it can be 2 here also. What you are going to see is the part is symmetrical about its principal axis, beta symmetric, then these are your second and your third digit 0, 0, right. So, if your first digit was 0, then you take this. If you take if your first digit was 1, you take this row, and if your first digit was 2, you take this ratio. So, I will repeat this again. This chart is for your second digit and your third digit. Okay. This is your second digit and this is your third digit. So, let us say that you chose, for whatever reason you chose 0 and 3. Your second digit was 0, the part is alpha symmetric, it is 0, and beta symmetric projections, we will see what those projections are on end surfaces only. If it is on the end surface, you are only choosing 3. But there are 3 options here. Which one would you choose? That depends on whether your what was the value of your first digit. If the value of your first digit was 0, then you choose this guy. If the value of your first digit was 1, you select this guy. If it was 3, you choose this guy. What are these 2 guys? The first one is E and the second one is CR. Once you have this, you can go back and estimate what your cost is. So, is the case here again, same story. So, the second and the third digit, if the first was 6, 7 and 8. Okay. So, let us say your second digit was 4 and your third digit was 1. Then which of these 3 would you choose? It depends on whether my first digit was 1, 2 or 3, that is all. Okay. And again, what are these? This is E and this is CR, that is all, right. Okay. So, there is a quick example that we will look at. So, first thing is, you know your feed rate, you assume 5-second cycle, and the component is given in this particular case. What is that? A over B, A is 30, meaning your length, B is your width and C is your thickness. So, A over B in this case is 30 over 20, which is 1.5, A over C is 2, 30 over 15. Why do I need this? Because I need to understand what my, so the component that I showed you is a non-rotational component. So, non-rotational component, you need to figure out whether it is a flat or long or cubic. So, in this case it was cubic, is that right? A over B was less than or equal to 4, yes, and A over C was less than or equal to 3, sorry 3 and 4 respectively, that was the case. So, it is a cuboid. So, cube, so my first thing is 6, 7 and 8, right. So, it should be 8, that is what we are choosing, it is 8. So, your first digit was 8. So, what did we see? If 8, there is one particular chart in which you go and see, but in order to do that, you have to take projections. Okay. So, what is the projection? In the 3 different directions you look at it. What are the projections? In the x direction. So, this is your x, you are seeing from this, this is what the projection is, and you see from the y direction, this is what your projection is, and you see from the z direction, this kind of top view, right. So, this is what your projection is. Now, how are we going to use all these things? If you go back to the chart, it asks all these questions. Part can be fled in and supported by a large end of protruding flange, all that, and what is this? Beta asymmetric projection step. No, I am just giving this as an example, but the same thing will be here also. Okay. So, the steps are chamfers parallel to what axis and all that we need to use. So, that is the reason we do this. So, now you will have to look at the projections. Looking at the projection in the x axis, the first one I am talking about, there is a step here, which can always be used to determine the parts orientation, because we will have some kind of a holding or an orientation scheme for the robot to, or the automated thing to work. So, in that case you can use this step as the criteria, and sometimes the groove also, and in this case only one orientation is possible. Okay. So, 4 is the second digit. In this case, part has no symmetry, there was no symmetry as we code the main feature that defines the orientation. So, my second thing was 4. Then I need to figure out what is my third thing, okay, whether it is 0, 1 or 2, how is steps or chamfers parallel to x axis, y axis, z axis. So, we will see what it says. Groove in the y direction or step in the z direction also can be used. So, there is a groove in the y direction or there is a step in your z direction, whichever you want to use. So, in that case what happens is your third digit, choose a feature that gives the smallest digit. If you have two things, then obviously you will choose the one with the lowest, because that translates into lesser time. Okay. So, we will choose 0 in this case. Now, I have 3, which one would I choose? It depends on my first digit. What was my first digit in this case? 8. So, 6, 7 and 8. So, I will take this guy. So, it is 0.15 for my E and 1 for my CR. Okay, that is all. So, 0, and from this you can get what your E and CR are. Okay. So, 840 is your 3 digit code, E is 0.15 and CR is 1. E is 0.15 and CR is 1. So, L 30 mm longest part dimension. This is again from a projection perspective, 30 mm was the longest dimension. So, how do I compute FM? 1500 times E over L. So, E is 0.15 divided by 30 mm times 1500, you will end up with 7.5 parts per minute. Since the cycle is 5s, that is the initial assumption that we made, it means that 12 parts per minute is what you can do. So, FR is greater than FM, hence you use this, you use with the FM part. CF is 0.03, 60 times FM times CR, you will get about roughly 0.24 units, cost units. So, I am not saying it is cents or dollars, or, so we are just using some cost units. So, 0.24 cost units is what we are looking at. So, but this does not, this is just to give you an idea how to deal with robotic assembly, how you can use similar concepts from manual assembly in the robotic assembly case also. But there could be additional feeding difficulties. For instance, the part can overlap. In robotic assembly this can happen, manual assembly you will find and you can stop it. This is easy to feed in such a case. So, you will have to come up with such things, meaning such solutions to avoid overlapping. But that is kind of taken care in the, for instance, parts do not tend to overlap during feeding, then it is a good one. Not delicate, it is delicate, under which it is non-flexible and flexible, non-sticky, sticky, just like very similar to what we did for manual assembly. Similarly, you can come up with these numbers. So, HS stands for high speed automatic insertion. Okay. So, the question is, we might not end up standing there and giving one component after the other. If it is a robotic assembly, it is an entire robotic assembly. It will pick the part, it will orient it, it will insert it, it will fasten it, the whole thing is automated, right. So, if the component is sorted from bulk and delivered to a convenient location, special purpose workheads can be designed for the assembly part. Such heads working on cycles that are greater than 1 second, your CI, the cost is 0.06 times 60, it is again the cost of the equipment per second, CI is times WR. Okay. So, what is WR? WR is the relative cost of any work head. Work head means one head per work, that is the work head, and it is inversely proportional to the feed rate, very similar to the other one that we, and directly proportional to the work head cost. So, your total cost now will be your CF plus CI. CF is something that we saw, CI is given here, it is in terms of your work head. So, the general guidelines, you want to minimize the number of parts that you want to assemble, as usual, no points for guessing. Facilitate the assembly by providing chamfers or tapers. So, it is easier for the robot to deal with from a projection perspective. They know what is x, what is y, what is z. avoid expensive and time consuming fastening operations. We might want to avoid any kind of holes projection that can cause tangling, that was seen here also, parts that will not tangle or nest, and attempt for symmetry, else exaggerate this asymmetry, so that you do not have to have a expensive vision system or deduction system to identify the symmetry. Okay. So, with that I kind of wrap up the discussion for high speed robotic assembly.